Next up is Heimir is going to talk about extending command and control for golf, greater orbit, larger footprint.
So I'm going to talk about protocol extension, and that I've been working on, and the current command and control setup is pretty straightforward. I mean, we have this program on the ground called AMCOM, and we simply send commands to the satellite, and it's kind of like, fire and forget. We don't know unless we get some kind of telemetry back that this actually took or not. And it works fine, and we've been using it since 2015. Okay, so for 10 years. So don't break it. I mean, so that's one of the aspects of this. And this is fine also because we have rather simple commands. And on the left there, you can see actually the Fox commands are, put it in safe mode, health mode, and so on and so forth. But when we are now working on golf, we need longer payload. We need actually bigger payload to be able to, command the satellite. And one of the main things is actually the ATCS. And in order to operate, the ATCS, we need to tell it the orbital parameters, for example. And in order to do that, we need to send all these parameters as a unit, as a single command, and then commit to it if everything comes across. We cannot just send willy-nilly, this parameter now and the other one, an hour later, and so on and so forth. So that is the challenge here. And we also have way more complex systems, like Kip is working on the power system, which is, in itself a pretty complex thing, and we might need to be able to interact with those systems. So that's the background of this. So what I suggest doing is to reuse stuff that we already have. I mean, it doesn't make any sense to throw away like AMCOM that has been tried and tested for 10 years. So keep the command uplink the same, but in order to be able to get some feedback on the progression of these transmissions, again, smuggle data on the telemetry downlink. And we already have a very good, telemetry program called FoxTelem. And we happen to have like 5 bits of data in the telemetry header that we can reuse for this purpose. And that's what I've been, working on. And so FoxTelem would actually then give us these 5 bits as feedback, coming from the satellite on every packet coming down. And then I only need, this piece, which is actually down there in the left part, which I call multi-part command, which will then assemble, these commands and put AMCOM more or less in, a slave mode, where actually I can send these packets. We already have some of that functionality, they are very similar to it, for the CAN commands that is already built into AMCOM. But the key thing here is that using exactly the same thing on the radio, and so we are not, risking any, bugs and problems, and at the same time be able to extend this. So, what I'm suggesting is actually that we take the AMCOM software command that's already there. It looks like this. I mean, each command is 50 bytes, and starts with a 6-byte header, and then we have these different things, including 8 bytes of payload, practically. it's now organized as 4 16-bit values, and so that's the the plan is to actually send multiple of these to actually get more data across. And a simple way to do that is to modify this piece. Offset number 7 is already the namespace. So we have a namespace, different namespace, and for each namespace we have different commands. And this is used for, like, we can give universities a namespace, and they can actually do whatever they want and introduce their own commands without messing with any of the commands that we already have to have. And we don't have that many, so we can split it up and say, if the most significant bit of the namespace is set to 1, then this is a multipart command. And then the flight software can actually, act differently if it's a multipart command, as opposed to all the other ones. So that's the extension piece. And then we need to be able to tell the flight software how many pieces are there and which piece is this, because we can lose packets. I mean, we can actually get, instead of actually packet 0, 1, 2, and 3, we might actually get no packet 0, but 1 and 3, and we have to be able to deal with that. And so the way to do that is actually to take what we have in the software commands now as 2 bytes for commands, and we've never actually used all of that, to split it up and keep the byte number 8 the same as a command byte. So now we have 256 possible commands. Out of 128 of them can be multipart commands, and then actually introduce this sequence byte instead of the second byte that we didn't use. So the sequence byte is split up into two 4-bit fields. The first 4 parts, obviously the most significant nibble, is telling the flight software how, what's the maximum sequence number for this. And that can be a number from 0 to 15. So we can have up to 16 parts. And then for each of these parts, we have a sequence number from 0 to 15. So that's the structure, and that's basically the idea. And everything follows from this. Pretty simple. So if you're sending a sequence that has 5 parts, so we now are actually be able to send 40 bytes. This would be what would be sent. So the first sequence byte would say 40, 4 meaning the last sequence is 4, meaning 5 segments or 5 parts. And then the 5-bit thing I was talking about in the feedback, telling me how this is going, would be something like this. So I need 4 bits to acknowledge. Or basically, what I'm doing here is I'm splitting this 5-bit thing into a single bit, saying, is this an acknowledgement or not? If it is, the following 4 bits will actually contain the information. And the information is actually what is the next missing part. Okay? So if it says 0, 1, it says this. It basically means that the second part is missing, because if the first part, which is number 0, would be missing, I would be sending acknowledgement to 0, and meaning resend 0, please. And and then in the end, when everything is working and everything has been executed, this acknowledgement goes away. Says, okay, I'm done, and the sequence number would be 0 for the happy path. Everything working fine. But I can also smuggle an error message, into those 4 bits. Hey, come on, we need to use it as much as we can. So So that's what's going to happen on the wire. How does this look? I mean, this is a simple sequence diagram of a transmission, and what I'm talking about here is actually the first part. If you read this from the top to the bottom, and the 00 at the top is coming from the spacecraft down to the ground station and saying 00, meaning I'm not in the middle of another transmission. So basically, I'm waiting until everything is clear in the spacecraft. Then I start to transmit, in this case, 4 segments or 4 parts, and I just send them one after the other. There's no reason to wait, because the telemetry is coming down, every 7 seconds or something. I can send seven parts without waiting. If I would be waiting, I mean, I would send and wait for 7 seconds, send and wait for 7 seconds. I mean, that doesn't make any sense. Let's be optimistic and say, okay, everything is fine. But of course it isn't. So, if it is, then we will get back, the acknowledgement saying the next segment is number 4. The ground station knows that, I don't need to send 4 because I mean it's only the 3 is the highest one, so it's one above what the last segment is. So I'm done. And then on the spacecraft we can execute that command with all that payload. And in the end, when in the next round of telemetry, I will get the 00 again. So we are ready to send another command. Okay? Pretty simple, right? If it fails, then the same sequence. I wait for a 00, blast these 4 segments up, and instead of getting a 1-4, meaning everything is fine, I get a 1-2. Oops! That simply means that the lowest number part that is missing is number 2. There might be 3 might be missing too. I don't know, but because I only have 4 bits, right? So I resend segment number 2, meaning the 3rd segment. And then it comes back with 1-4, saying, hey, I'm good. And this can be executed on board. Make sense? Really simple, right? So, so then what I did, I sat down and wrote down on paper the actual algorithms for this. And in the beginning, it was really simple, okay? And then I began to think about, what about this case? And so in practice, what this is, and you can read about this and the description of this in the actual paper that's going to be in the proceedings. So if you want to lead, want to know all about these details here. But the key thing here though is that we need actually two threads of execution. On the ground station. One is actually the thread that is sending the data, and then there's a separate thread that is actually receiving the telemetry. And then they have to talk to each other. And basically, this algorithm, this send MPC algorithm, will actually use the acknowledgements coming down to send these things in the order I was describing. Just trust me on that, okay? But by the way, I actually have a simulation of this algorithm that I'm going to show you because I didn't believe it myself either. So the receive is a bit more complicated, but this is actually what. No, I mean we can do it together, right? So yeah, but the actual each of these pieces are not that hard. But again, there are two threads of execution here. The one that is actually just, getting one part to receive here on line 25, and that actually there's a segment coming in, and this algorithm also is simple in that sense that we can get these segments in any order. we just have to have memory on the spacecraft to store all of these 128 bytes. That is the maximum size of the payload. But but it can come in any order. Again, like I said, one thread is actually the one on the left is actually the main thread. But then there's a separate thing that is called by the telemetry thread that actually takes the status of what's going on, what has been received, and transmits it down. But this was great fun to work out. And okay, a little bit about the payload that we can now send. Currently, well, like I said before, we organize everything into 4 16-bit integers, basically. But there is no reason to. And so one way of doing it is actually, to have these different data types, and we need them. For example, if we're going to send like the orbital parameters, those will be double precision numbers, floating point numbers, and in other cases we might be okay with like a regular float, not double precision, and then we can pack 2 of them, and so these are just regular data types that we could actually put into these packets and look at them as a single payload. In the beginning, we would have to just be careful when we define these. Us meaning the engineering team, to actually make sure that we are not crossing a boundary on the 8-byte packets, but that's a minor thing. Okay. So and then we would actually need to define a command, and this is one way of doing that. Currently, we have a CSV format called satcommands.txt, but that's going to be really hard to squeeze this in. So I suggest that we just switch that over to JSON, which is easy, and then we will have something that's really readable for a human and easy to maintain. So in this case, this would be a command sending a subset of the orbital parameters up to the satellite. And it would say, okay, the namespace is 80. Okay, that's just a fictitious namespace, but it has the high bit set. Command number 1, the list of satellites that this applies to, Golf T in this case, can be a list. Golf 1 and so on and so forth. And then I'm talking about the data file name because, say, if this is being derived from a TLE, I would rather have a program write the CSV file, and which would be written, read by this and sent out, rather than trying to put this in by hand. That's stupid. So that's one of the things that is extending this, and then of course the actual parameter names and their data type. So in this case, they're all floating, 64-bit floating points, or at least double precision. And so that is how, this is an example of how this would look like. Of course, we would, work this out in, depending on the target system on the spacecraft, what exactly we need to send. But another, connection that Burns, of course, pointed out really early on, hey, are we then going to do all this by hand? But of course not. We would generate, some header files for the flight software based on this input, so we don't have to do it by hand. And we, when we change something, that will actually be automatically, compiled into the flight software. Okay. This is basically the last slide, is it? Yeah, okay. Yeah, so what I did was, like I said before, I wrote a simulator to convince myself that this actually did work. And it was mostly about the timing, because okay, I can send 1 packet per second. If you think about, 100 bytes at 1200 bao. That's about a second per packet. And then we get telemetry coming down every 7 seconds. In the beginning, I did not synchronize between the telemetry downlink and the transmission, but in this algorithm I do. And that is actually a good thing. But you can see the simulator. I mean, it's just a simple multi-threaded Python thing, and it's on my GitHub. So, and there's a link there, in the GitHub to the paper itself describing this. So, this is a dangerous thing, really dangerous thing. Okay. So this is the simulator, and it's showing if I'm sending 7 parts to the satellite. In the beginning, they're all red because none of them has been received. The numbers here are actually how many times each segment has been sent, and then I have this error rate here, which is something it's basically the probability of a packet loss. So now it's set to like 10%. So there's a 10% probability that I send something to the satellite and it's just dropped on the floor. And to make this actually more realistic so we can actually see what's happened. The transmission status is shown here. And you might see actually that this color is changing every 7 seconds. Now it's green because there was another, and the empty set thing here actually saying is this is the 0, 0, as opposed to ACK for a 0. Okay, we'll see that. Okay, so then I started, and the simulation will start, or actually this will start when the transmission status changes. Okay, so I got these, packets coming down. Oh, all of them. Okay, and then I get ACK for 7, and I'm done, right? So this was easy. But I don't have to go that far. I'll just go up to 20, and that's enough to, to get some errors. Yeah, but okay. Now you see, these. Hey, what's going on? Come on. This never actually. So this would always fail. When I was doing this. Okay, 30%. And okay, yes, this see 0 failed, and okay, so now you can see it's asking for 0. Say, hey, give me 0 back, and then it will ask for 4 once it gets number 0. Okay, it was sent twice, and now it's going to ask for 4 in the next packet, and it went green. Okay. It only needed to send, these 2 packets twice, and otherwise now it's asking for 7, saying I'm done. But if we increase this really, it's like, now it's like 50-50. And okay, 0 went through, but and this is going to take a while. Again, because I blast all the packets in the beginning, hoping that everything comes through. But in this case, okay, it's not too bad. It only had to send these twice, but I've seen this. Have to send 2 or 3 or 4 times, but it's still asking for 3. Okay, yeah. So like number 3 did not come through. It's been sending it 3 times now, and so this is okay. Now it finally made it. It had to send it 4 times, and so we actually don't want to operate, when we have like 50% packet loss. That's basically what this is saying.
Maybe real world better, right?
I know. It is. But but the thing is, if we wait long enough, it will come through. Yes.
So you can send like 1 second, but when you have to redo it, you have to wait 7 seconds.
Yes. Absolutely, because I don't know which one was missing. Okay, and this simple algorithm will tell me what is the lowest number that's missing. So it always goes from left to right, so yeah, okay.
Why wouldn't you just keep sending subsequent ones until you get an add back and say, oh, I missed one, or I can skip ahead?
We could do that, yes. Yeah, because I mean we're basically sitting doing nothing for 6 seconds. Yeah, I know. And there are so many. I mean, even though this is a really simple thing, hey, I mean there are so many edge cases that. But that's why I actually decided to write this as a simulation to actually see it. Okay. Okay, that's it.
Any other questions?
Very good presentation, thank you. Given the attack on satellites these days by malicious actors and malicious nation states and non-state actors, is there any plan to put encryption or other cybersecurity mechanisms in place, both on the uplink and downlink?
Okay, so the uplink is already, we already have a digital signature, so you cannot actually just blast it. And so it is protected that way.
Yeah, look at my paper from several years ago. Yeah. That's what we're doing. It is the uplink signal is encrypted. The downlink signal is forward error corrected, but we don't care so much.
It's against FCC regulations to encrypt anything on the amateur bands with the intent to obscure other than uplink commands.
Yep.
You can't encrypt the downlink no matter what.
Right. But yeah, you can see here actually, out of the 18, I mean, we have 18 bytes of actual data, followed by, the signature, which is 32 bytes. So the signature, and one of the, you cannot either copy this, because, I mean, there's a timestamp that is increasing. So you cannot do, like a copy attack or anything, right? So, but it's a good point. But I mean, denial of service attack is another thing. I mean, somebody can just blast with signal and descends all the receivers, and that would actually stop us. But yeah, good question.
Any more questions? Thank you so much.
Okay.